Multiplexing. Multiplexing is a method for combining multiple signals into one signal going over one medium, one fiber for our purposes. In a practical sense, multiplexing enables streaming of multiple videos across a single fiber. In multiplexing, the capacity of the fiber is divided into several logical channels, one for each data stream to be transferred. On the receiver end, a reverse process called demultiplexing extracts the content sent on each channel. In wavelength division multiplexing, or WDM, a multitude of different wavelengths is transmitted across a fiber. This is great for increasing network capacity. Instead of having X more fibers in a transmission line to send X more data at the same time, one can just send across X wavelengths instead of one wavelength using WDM. The benefit of this is that one can increase network capacity by a considerable amount without having to lay extra fiber, an expensive process especially if it's a transoceanic line. In an ideal world, you could just have as many channels as you want going across a fiber. We do not live in an ideal world, however. Ours is filled with many unhelpful physics phenomena. One of these is the tendency for signals to give or take each other's power when traveling together. It's as if there are a lot of people crammed onto the tube together, silently competing for room with each other. A measure of how much signal power jumps between neighboring channels within a multi-channel system is called crosstalk. Crosstalk can also refer to several effects in WDM systems. UCL specializes in alleviating loss of transmission quality due to these phenomena. One such effect is four-wave mixing. This is where neighboring channels interact with each other and generate additional tones nearby. If there's a lot of channels working close to each other, these extra tones will overlap with real data, introducing interference into the system, ruining the data. Thomas Girard of UCL Optics Group says we can correct for this effect by performing numerical simulations of the nonlinear Schrödinger equation to model the generation, then correct for it after reception. This is called digital back propagation and is one of our specialties. The same method can be used to correct for an event called cross-phase modulation. Furthering wavelength division multiplexing involves figuring out how to correct for these effects adequately, and is essential to let us send more data across networks without having to lay additional expensive fiber. This is data we need for a growing population and the developing Internet of Things.